All right, guys. In the last section, one of the things that we did was we covered electrical power. And we found that the power is the product of the voltage across an element times the current that flows through it. However, we had to be very, very careful to observe the passive sign convention. So one of the things that we can say is this is actually going to be plus or minus I times V. And whether it's plus V times I or minus V times I, it depends on the picture that you have, right? On top of that, we did state that if the power was negative, by the end of a calculation, then the element is a load, or I'm sorry, a source. Let's revise that. So this is, the element is a source of electrical power it is generating. I know it seems counterintuitive. Negative power you would associate with something being consumed, but that's not the case in terms of our interpretation of the power. Conversely, if something by the end of a calculation had positive power, then the element was a load, and this load would be consuming electric power. Now, one of the things that I want to go through is an example. Right? And in this example, we have two circuit elements, A and B. And they're represented by black boxes. So over here we have A. Over here we have B. And they're interconnected in the following manner. There's a wire that runs and connects the two elements like so on the top, and there's a second wire that runs like so. Furthermore, they define for us already a voltage across the two wires like this with that particular polarity. That means that this top wire is at a higher voltage than this bottom wire. And there's a current that flows through the top wire like this and going from element B to A. And the question is to calculate the power of the interconnection and state whether power is flowing from A to B or vice versa. And they give us what the measured voltages and currents are for four separate cases. For case A, the current is measured to be 10 amps, while the voltage is measured to be 125 volts. For case B, this is measured to be positive 5 amps, while the voltage is measured to be minus 240 volts. For case C, this is measured to be minus 12 amps. The voltage is 480 volts. And lastly, for case D, the current is minus 25 amps and the voltage is minus 660 volts. So one of the things that we can do, and this is part of our solution, is regardless as to how these voltages and currents in terms of the numerical values, how they happen to be defined, one of the things that we can do is we can kind of draw, quote unquote, and this is not a technical term, this is something that I'm borrowing from my physics days, kind of a free body diagram of the elements A and B, the circuit elements. So one of the things that I can do is I can kind of cut using an imaginary pair of scissors through those two elements to kind of separate them out, and then investigate what's going on individually with A and B separately. So over here, A itself, with no reference to B, would look something like this. Now keep in mind that the voltage still must be respected. The top wire is still at a higher voltage than the bottom. And based on the direction of the current, notice that through the top wire, the current must be flowing in to A like this. It's going to flow through the element, and then it's going to flow back out in this direction. Right? Similarly, for B, we have the two wires like this. The voltage across the wires must be like that. And notice that this current up here is flowing out through the top wire. So it must have originated down here and flowed up that way. So here we actually have a current that must have originated down here like this. It flows through the element and then it shows up there. Now notice that we can actually write the power equation for each one of these. Now for this one, notice that this current is going in the direction of the voltage drop. Why? Because it's originating there, flowing through, and ending up there. Now, because it's going through a voltage drop, there is a sign associated with this equation. This one is positive. Conversely, on this one, notice that this current originates over here, goes through the element like this, ends up there. This one is actually going through a voltage rise. That means that in this relationship, you must add in that minus sign by hand. Right? So each one of these separately are the equations that we're going to use to calculate the power associated with element A and the power associated with element B. So just to denote that there's two separate equations that we're using. This is the equation for element A, this is the equation for element B, and I'll box these. For the first one, you never put in a minus sign by hand. For the second one, you have to always put in a minus sign by hand. Now we're in a position to start calculating some of these powers for each case. So here, for case A, we have the current is 10 amps, and the voltage is 125. So PA is plus the voltage times the current, so that is 125 volts times 10 amps. This is positive 1250, and this is in watts. For B, I have to add in that minus sign by hand, and I have 125 volts times 10 amps. That is negative 1250 watts. Now notice that it is this sign at the very end that tells you whether something is generating or dissipating power. So over here, one of the things that we can say is A is positive. That means that this is the load. The negative means that this is the source. So the source is generating the power, the load is consuming the power. That means that this energy or this power is flowing from B to A. Let's take a look at B. So PA and PB we can calculate again, right? Except now this time B I is 5 amps and voltage is minus 240 volts. So here for A, we're using the same equation that we had previously, this one, with no minus sign. So that is 5 amps times minus 240 volts. Notice that I switched V and I. That's perfectly permissible. Multiplication is commutative. So notice here you end up with a minus sign answer. And 5 times 240 is 1200. So this is minus 1200 watts. For B, I must add in that minus sign by hand, and it's 5 amps times minus 240 volts. Those minus signs cancel, and you end up with 1200 watts. That means that this is the source, this is the load, and energy and power, similarly, is flowing now from A to B. We can play this game again. We'll have PA and PB. So for that voltage and current, I is negative 12 amps, voltage is 480 volts. So here for PA, we have plus minus 12 amps times positive 480 volts. Let me pull out my calculator to calculate that. I can't do that in my head. So 12 times 480 is minus 5760 watts. Similarly, for PB, I add in the minus sign by hand. We have minus 12 amps times 480 volts. That yields positive 5760 watts. That means that this is our source. This is our load. I said load, I wrote lobe. Let me correct that. So this is the load. And here it is flowing from A to B. Play the game one last time. So PA and PB. We have the voltage and current as negative 25 amps and negative 660 volts. So negative 25 amps, negative 660 volts. And then here for B, I have to add in that minus sign by hand, minus 25 amps, minus 660 volts. And this will end up being positive, this will end up being negative. You have 3 negative signs there that multiply all out to a net negative. Let me pull out my calculator. So 25 times 660, that is 16,500 watts. This is 16,500 watts. So this one right here with the positive sign, that is the load. This one is the source. So here energy and power are flowing from element A to B. Now there's a few things that I want to point out. Once again, notice that when it comes to whether something is a source or a load, does not depend solely on this. It is the final signs by the end of all of the calculations, all of those signs that determine whether something is a source or a load, right? So just because you see a minus sign here, right, does not make that element automatically a source. Right. Similarly, over here, just because you see a positive sign there does not automatically make the element here inside of the box a load. It is the end sign by the final calculation that determines whether something is a source or load. Another thing that I want you guys to observe, and this is a very general feature of any power calculation. If I, for the entire system, so the entire system consists of element A and B, if you add the powers for this and this, for example, you end up with 0. If you add this power and that power, you end up with 0. If you add this and this together, you end up with 0. If you add this and this together, you end up with 0. This is an extremely important feature of every single power calculation that you end up doing, right? And it is that the total amount of power must be conserved, right? There's a power check. And what that means is if you add up all of the positive powers that are being generated, and you take the absolute value, they must equal the absolute value of the total power that's being consumed or dissipated. This is what they call the power check. And it is, no matter how large your system, the total amount of power that's being generated by all of the elements must equal the total amount of power that's being consumed by all of the elements. Right. This will do for the example. And I hope you've found it useful, and we'll see each other in some of the other recordings.